what I have is a simulation that can show how the force of gravity can affect a field here with multiple masses. So if I start the simulator, you can see uh, these masses are going to slowly converge towards each other. And each one has its own specific uh, force that's being exerted on it. This yellow ball here is being pulled up by the green ball up in this direction. It's being pulled up in this direction by the pink ball, and the blue ball is pulling it in this direction. So this object is being pulled in these three directions because you have three different masses. Now, depending on the size of the masses and the distances away, is going to affect which one has a more powerful effect on the object. Right now, we have the masses equivalent, so because the green ball is closer, it's going to pull on the yellow ball, uh, and that's why the yellow ball is being pulled towards the green ball at a faster rate than it is either of the other ones. If I reset this and maybe make the blue ball bigger, so let's make that a bigger mass, you can see the effect of the green ball is not as great on the yellow ball. The blue ball is now starting to tug on the yellow ball with a greater gravitational force. And you can see that the yellow ball is being pulled towards the blue ball at a more rapid rate as well. We are going to take a look, take an analysis of these objects. We're going to do it in a static fashion, meaning we're not going to set everything in motion. We're just going to see what the effects are, assuming that these things are not moving yet. So if before we set them in motion, there's still, the force of gravity acting on it, but we're not allowing it to set in motion. If we started it and allowed these things to converge on each other, you're going to start to see as these things get closer, their force of gravity is going to be different. So they're going to get pulled at a higher acceleration. That's because the distance between them is shrinking and shrinking as they pull closer and closer together. And you can see that happening. And as these things converge, they start to rotate around the larger masses, so the dynamics change. So we're not going to get into that as much as we are, uh, you know, let's analyze it before these things are set into motion. Okay, so what we have are four objects sitting in some plane, and we're going to determine the resultant gravitational force on the object D. What that means is we're going to figure out what direction and with what force this object's going to get pulled at initially. Remember, it's not just going to get pulled by A, it's not just going to get pulled by C, it's not just going to get pulled by B. There's going to be some resulting force that initially starts pulling this object, okay, and at some angle. Now, it's going to have some magnitude of force pulled by B, okay, in the direction of B. It's going to have some magnitude of force being pulled by A, and some magnitude of force being pulled by C. And we're going to determine what each of these forces are, sum up all the forces, and come up with an x and y component for some resultant force. And we're going to figure out what direction that takes. Uh, First thing we need to notice is that we have a rectangle here, and take a look at our dimensions. We could probably figure out an angle right here that B and D are interacting with each other because this is making a right triangle. The line in between them makes a right triangle. So this angle here, theta, theta is equal to some component of these two objects. Now we have our opposite side and we have our adjacent side. Units don't matter as long as they're the same because they'll cancel out anyway. So the tangent is opposite over adjacent. So if we know tangent is opposite over adjacent, we can figure out the angle. And we'll get that by taking the inverse tangent of both sides. So the inverse tangent of opposite over adjacent will give us the angle. And we'll find that theta is equal to 21.8 degrees. 21.8 degrees is this angle in here. Okay, so the reason we want that angle is because this force, the force of B acting on D, the force of gravity from B acting on D, is in two dimensions. This is the force of gravity of B acting on D. And that's in two dimensions. So we're going to need the angle in order to break it up into its two dimensions. And we can see this is multi-dimensional. So there's two dimensions going on here. You've got a y direction and an x direction of forces acting on B. We're going to add the vectors mathematically, sum them up, and figure out the components of the resultant vector. So let's label the rest of our forces. This is a force of gravity for A acting on D, and this is the force of gravity of C acting on D. Now, force of gravity is equal to, besides the fact that it's equal to m mass times acceleration due to gravity, it's also equal to our gravitational constant times the mass of object 1, the mass of object 2, all over the distance between them. We call that the radius squared. And if we have three objects, we're going to need three different forces of gravity. We're going to have the force of gravity for C acting on D is going to be equal to force of gravity of C acting on D is going to be G mass of C mass of D all over the radius between C and D squared. And if we plug all those numbers in, we will find we have G, the gravitational constant, times 8 times 12. 8 is the mass of C, 12 is the mass of D, all over 2.5 millimeters, which is 2.5 times 10 to the negative 3 squared. And we're changing that times 10 to the negative 3 to change this units to meters. And we can calculate. I'm going to leave G out of this for now. We're going to leave this in terms of G. When you do your calculating, you get the force of gravity of C acting on D equal to 1.54 times 10 to the 7th times your gravitational constant. And again, we're just leaving the gravitational constant as G. A little easier than having all the scientific notation stuff floating around. Sometimes it's just easier to leave it as G, and then at the very end, we'll multiply through by G to figure out what our values are. That's how you get C to D. It's no different than what we did with figuring out the force of gravity before. So figure out the force of gravity from B to D and A to D, and take a second to figure those out, and I'll show those values next. So your force of gravity from A to D and from B to D are as such. Keep in mind, in order to get this distance from D to B, you're going to have to take a squared plus b squared equal to c squared, and take the square root of both sides to get your the distance here between D and B, and you will get 2.69 millimeters. So 2.69 millimeters. And we have our forces here. Now, we can't just add up all these forces and say that's the force acting on D, because they're all acting in different dimensions. So we have to figure out what forces are acting in the x direction and sum up our forces that are acting in the y direction. So we got to take this and split them up into directions of x and y. In the x direction, we have the force of gravity from C acting on D. So you have the force of gravity. So if we're going to sum up our forces in the x direction, we've got a force of gravity from C acting on D. And whatever the x component of B acting on D is. Whatever the x component of B acting on D is. So F, B, D in the x direction. And just to back up real quick, this force BD is acting at an angle, again, of 21.8 degrees. At 21.8 degrees. Okay? And we don't need to worry about negatives for these. These are both positive and positive directions, so we're good there. And the sum of forces in the y direction, we've got the force of A acting on D, that's in the positive y direction, so we've got force A, D, and we've got force of gravity from B to D in the y direction. So the net force in the x direction, C, D, and this is the resultant force in the x direction. We've got that, plus this is going to be whatever the force between B and D is, times the cosine of its angle, times the cosine of its angle. Why cosine? Because it's measured from the x. Cosine of 21 is going to give you the x component, the adjacent component of your BD vector. And over here you'll have FBD times sine of theta. Okay, and again, this is your resultant x, your resultant y. We know the force between C and D is 1.54 times 10 to the 7th. 1.54 times 10 to the 7th. Plus force BD is 2.49 times 10 to the 7th times cosine of the angle, 21.8 degrees, and times G. So that G has to stay in there. We multiply all these and add up our like terms, and we see that the net force in the x direction is going to be equal to 3.85 times 10 to the 7th times our coefficient, our gravitational constant. And our net force in the y direction, when we plug all our numbers in there, we're going to have 1.2 times 10 to the 8th plus 2.49 times 10 to the 7th sine of 21.8 times g. And we add those up. And we multiply here and add up. Don't forget to, when you add this, the exponents have to be the same, so you're going to have to adjust your decimal to make sure this is 10 to the 8th, or adjust this decimal to make sure this is 10 to the 7th. Either way, you'll get 1.29 times 10 to the 8th times g for your net force in the y. So this is our resultant force in the y, and this is our resultant force in the x. So this object is getting pulled by that amount in the y direction and that amount in the x direction. So these are your components of the resultant force. So your net force is going to be equal to, the net force vector is going to be equal to Pythagorean theorem. Square root of your net force in the x direction squared plus the net force in the y direction squared. And we'll call this the resultant force acting on D. The result force acting on D is equal to the square root of 3.85 times 10 to the 7th squared plus 1.29 times 10 to the 8th squared, and add them together and square root them both. Just adjusting the exponent so that they match up. Now we'll put our G constant in and figure out the true magnitude of the net force acting on D. And we'll find net force is equal to 9 times 10 to the negative 3 newtons. Now, that's the magnitude. To figure out the direction, we need to take the inverse tangent. To find the direction, the angle that that's acting at, we'd take the inverse tangent of our net force in the y over the net force in the x. Plugging these in, now we can eliminate the g's because you'd have a g over a g and they'd cancel out. You're going to find that your angle is 73.4 degrees. So this is 9 millinewtons at 73.4 degrees. Not a very strong force. And why is it 73 degrees acting for this resultant force? Let's draw our resultant force in green. So we've got our resultant force here. That's acting at 73 degrees. Okay, and that's acting at 73 degrees because A is pretty big in comparison to C, and it's closer to D, so it's going to have more of an impact. Okay, the smaller that R is, the greater the force of gravity is, and also the greater the object's mass is, the greater the force of gravity. Now B is going to have some impact on this and pulling it this way as well because B is a pretty, massive object, 1.5 times larger than object A, so it's going to pull it this way some also. But that makes sense where our vector landed. That's an easy way to check. Is just check and make sure that your angle makes sense. But that's how to deal with objects in a two-dimensional plane. You can have objects that make up a rectangle, so we could eliminate A and see what the forces of acting on D are, and as a result of B and C. All kinds of configurations. You just got to do a little bit of geometry to determine, which direction these things are acting, and add up your x components and y components, and then do Pythagorean theorem and your trig to get your angle.